So today we are going to try to have a bit more fun. So as I promised, we are going to talk about physics. So the first problem I would like to talk about is a general problem that is related to what we have been solving yesterday. So imagine that we have our favorite two leads and the scattering region, the resonant level, or whatever you want in here. So let me put it in general as a black box, right? So in here you can have whatever you want. And then you want to describe transport through this system. Now, you should realize that when people started thinking about transport through these nanostructures, and that was, in the past century, in the 60s, when people were interested in transistors and things of this type. The standard formalism for transport was Drude formalism or Boltzmann equation or things of this sort. And it's clear that if you start describing transport through this resonant level, for example, using a Boltzmann equation is going to be a nightmare, right? Because, well, you will have to do a semi-classical approximation, then describe tunneling. It's a mess. But then came a guy whose name is Rolf Landauer. I actually realized that you could think of transport through such systems, as I already told you, as a scattering problem. So you could just think about transport as some incoming free electrons entering a scattering region and then getting out as free electrons. And the only problem you had is figuring out how to compute the current as a function of what? Of course, as a function of the scattering matrix or the matrix elements of scattering through this, scattering region. Right, and he came up with a pretty famous formula, which is the Landauer formula that states that the current is equal to E over, so this is an E over H, times the integral over d omega over 2 pi f left of omega minus f right of omega times the absolute value of t of omega squared. Now, this formula is strictly speaking valid only for non-interacting electrons. So what I'm assuming is that here I have something, but it's non-interacting. So electrons are not interacting in the scattering region. There is maybe a quantum dot, some geometry, I don't know what, but there are no interactions. And therefore, what I can do is think about the problem of transport through, yes? What is E? T of omega. I'm going to explain it in a second. And therefore, you can think of the problem of transport, as I said, as a scattering problem. And if it's a scattering problem, then it's going to be characterized by a transmission amplitude and a reflection amplitude. And, well, you might have some breaking of left-right symmetry, so you might have an additional phase, but this is in general what it is. And then Landauer said, okay, take the transmission amplitude, take the absolute value squared of the transmission amplitude, which is the transmission probability, and then what you do is you essentially think of transport in the following way. You want to compute what is the transmission probabilities of all the electrons that can go through. And the electrons that can go through are the ones that have nothing on the other side, right? Because of Pauli principle. So this guy here, of course, cannot go here because, well, this is field. Very simple. So only this layer here, And therefore, you take the difference, you multiply this T of omega by the difference of left and right Fermi functions that describe essentially what are the empty states on the other side, and then you take the integral and multiply by E over omega. Now, this formula, if you take the limit in which mu left minus mu right is small as compared to what? Well, let's say smaller than temperature, which is a simple parameter. You cannot say some parameter is small in physics. It's always small as compared to something else. So otherwise, it doesn't make any sense to say it's small. So let's say it's smaller than temperature. Then I can expand F left minus F right as mu left minus mu right times minus F prime of omega. The minus comes because the chemical potential enters with a minus sign in the Fermi distribution. And then, well, this is just a voltage bias, EV. And you see that if I do so, this formula becomes E squared over H integral d omega over 2 pi minus a derivative of a Fermi function times T of omega squared times V. And therefore, yes? Well, so F, if you, F left is what? F left of omega is equal to the Fermi function of omega minus mu left. Let's take the Fermi function without a chemical potential. F right of omega, well, is equal to the same thing. And now I'm assuming that I just do the Taylor expansion, right? In the difference, so I take mu left equal to mu bar plus mu left minus mu right divided by 2, mu right equal to mu bar minus mu left minus mu right divided by 2, and I expand in this. And that's what you get. Okay? All right. So now, if you look at this, you immediately recognize standard linear response formalism, right? So you see the current is proportional to the voltage, and what is the constant of proportionality is the conductance that usually has the letter G. All I've done here is for spinless electrons. If I want to put spin, then I put a factor of 2 in front of everything, right? For spinful electrons. Now this object here is called the dimensionless conductance, G naught. Because you see that everything here, so this integral here, sorry, it's called the conductance quantum. Because you see that this stuff here is dimensionless, strictly speaking, because this is the omega and this is the df d omega. So everything is dimensionless here, and all the dimensions are sitting in this prefactor. So, for example, when you study the quantum Hall effect, the resistance is quantized in units of the inverse of this, right? So you have the conductance. And, of course, I mean, if I normalize the conductance by G naught, I obtain the dimensionless conductance. So if you're interested in what I call Russian physics, which are all the story of localization, weak localization, corrections to the conductivity, diffusons, couperons, and all sorts of things, well, you will always be dealing with this guy here as actually a large parameter of all your approximations. right? So you need to have a dimensionless conductance that is large. All right, so you see, it's a very smart idea. It gives you an opportunity to have a formalism that connects the solution of a simple scattering problem to the solution to the calculation of either the conductance or the current itself, if you're out of the linear response regime. Now, this formalism was later on generalized by a number of people. So, of course, Rolf Landauer, Markus Büttiker, Joe Imrie, and then many others. I mean, you can read about all this physics in a nice book by Joe Imrie, which is called The Introduction to Mesoscopic Physics. So I'm very proud to be cited in the, thanks to blah, 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 and Alessandro Silva, because I was a student and I had to read it to check the mistakes. Right? So that's how professors use students sometimes. So anyway, it's a nice book. It's very, very simple. No Keldysh, nothing. It's just intuition and formalism, nothing else. Right. So, okay, so what do we want to do now? Well, the thing is, imagine that we are interested now in applying this formalism to our scattering problem. And our scattering problem was the resonant level model, right? So of course you can apply it to anything. For example, if you want to take your favorite potential barrier in here, you can do that. You can put 2 potential barriers, 10 potential barriers. You will not be able to write any paper about this because all of this was done and beaten to death by people 50 years ago, or 40 years ago. So forget about it. But for fun, you can do whatever you want. Nevertheless, you can think of this problem and ask yourself, okay, what is the transmission probability here? Okay, so this problem, finding the scattering matrix for this particular setting, was solved by Langmuir, the same Langmuir as yesterday. He was actually interested in something different. He was interested in impurity problems and in some, relations between scattering phases and occupation of the levels. Never mind. But the bottom line is the following, and I'll tell you just the result. So I'm not going to derive it for you. The bottom line is that the scattering matrix, which is a 2x2 matrix because it's, I have just 2 channels. I mean, I have just 1 channel per thing, is a 2x2 matrix. And as usual is 1 is the identity minus I times the T matrix. The T matrix is called a transmission matrix, I don't know. And it turns out that the T matrix, not surprisingly, is equal to, assuming that the tunneling matrix elements are not dependent on K for simplicity, okay? Well, you can put the dependence on K, but then life becomes a bit more miserable, is pi times density of states times V alpha, G retarded, V beta. So this is the matrix element, alpha beta. So this is the density of states in the leads. These are the tunneling matrix elements. This is the retarded Wien function of our resonant level that we computed yesterday. You remember, is a simple pole 1 over omega minus epsilon naught plus I gamma. So if we now take this and write it explicitly, you will get that this is 1 minus I gamma left G retarded minus I square root of gamma left gamma right G retarded minus I square root of gamma left gamma right G retarded and 1 minus I gamma right G retarded. Okay, so now, well, you see that if I now take this expression, but so the only thing I have to do is to take the absolute value squared of square root of minus I square root of gamma left gamma right G retarded, which is gamma left times gamma right times G retarded times its complex conjugate, which is G advanced. So it's G retarded times G retarded complex conjugate, which is gamma right, gamma left, G retarded times G advanced. Okay?
That matrix element of T, how does one write that down? Like you have to do the calculation.
Well, you have to do the calculation, yeah. So it's, but intuitively it's quite clear, right? Because, so you're computing essentially, you're figuring out how a particle that is created in the left is getting out on the right, let's say. So it's pretty clear that this is going to, so the scattering matrix elements should be V, so that this tunneling vertex, V alpha, V left, times V right, times the green function that sits in the, sorry, yesterday I used a different notation, times the green function of the scattering region. Because you have to create it in the scattering region and then remove it from the scattering region. And this is G retarded. So in a sense, I mean, you have to do the calculation, but the result is quite obvious, up to the minus I. Yes? Sorry? What is the statement? This is the S matrix. This is the statement. This is the scattering matrix. So, and maybe I have to remind you that the scattering matrix is, for this particular symmetric problem, is reflection, transmission, transmission, reflection. So this is the transmission coefficient of a particle impinging from the left and getting out on the right at some energy omega. And of course, if you do the opposite, you get the same because I have time reversal invariance. And then, well, and the two reflection coefficients. Yes? So how to generalize this to a two-dimensional situation? Well, you know, the question you're asking physically, it's not very easy to answer. So because if I think about it, how would I do it? So let's say I have a two-dimensional electron gas. So what I have to do is I have to gate it here and then gate it here, right? And then, well, of course, if you go to spherical harmonics, right, which is what I would do, then you just have, since you have spherical symmetry, you have S equals 0 channel. And then in that channel, you have to figure out what is the scattering matrix element that connects these two boundaries. An annular structure, yeah, this is called a Corbino ring, but this is typically, so this is an experiment that is done, for example, for quantum Hall effects. The thing is that typically in a Corbino ring, you don't gate the two boundaries. That is too complicated. So people never thought about the problem you're interested in. And moreover, here, you know, if I put just a center here, I'm pretty sure that you can get, you know, you can do the whole calculation just using the S equals 0 channel, If you put the two rings, I mean the two boundaries, then it gets more complicated. So you have to, it's a bit of a problem. Right, so, okay. So bottom line, this is how you calculate your transmission. And all of this is true for non-interacting electrons, right? So let me point out that this is gamma left times gamma right. So if you spell it out, omega minus epsilon naught squared plus gamma left plus gamma right squared. So that's what it is. And now comes the question, wait a second. Yeah. Now comes the question, okay, well, so far so good, but what about interactions, if I have interactions inside my scattering region? Is this what I'm going to get or not? Well, and now comes the trouble. So the generalization of this formula with interactions, which is the calculation I will do today and can be done with Keldysh. So generalization with interactions is due to Ned Wingren and Igal Meyer. And in my opinion, is a cute result. First of all, because it's useful. It was very useful to compute conductivity through interacting quantum dots in the Kondo regime, out of the Kondo regime, and in many instances. But second, because it allowed us to understand something important, something very important physically. So let me give you the final result, and then we will calculate it, okay? So we'll get through it in a few steps using Keldysh. So you will see where it comes from. But the final result is the following. The current is equal to E over H integral d omega over pi 2 pi f left minus f right times T of omega. Now, what is T of omega? T of omega is equal to gamma left times gamma right divided by gamma left plus gamma right times A of omega. A of omega is the spectral density, what I defined yesterday. This is an omega, is not this weird thing. What I defined yesterday to be minus twice the imaginary part of G retarded. Okay, so you might say, well, it has the same form as yesterday. No difference as yesterday, as before, no difference whatsoever. But this is incorrect. So it turns out that in general, T of omega is not equal to the absolute value squared of the little t of omega that I wrote down before. You can check yourself using, the general fact that you can expect that for an interacting system, typically what happens is that your G retarded becomes 1 minus omega minus epsilon naught. Let me rewrite it here. G retarded is equal to 1 minus omega minus epsilon naught plus I gamma minus sigma retarded. Sigma retarded is the retarded self-energy. Now, for those of you not familiar with this, this is just a solution of the Dyson equation I wrote yesterday. You remember that I wrote this plus this, that, and that I told you that convolutions of objects in the Keldysh formalism, if I have retarded, it's product of retarded Green functions. So this is going to be retarded, G naught retarded, G naught retarded, sigma retarded, G retarded. And these are going to be convolutions. Now, if you take a train translational invariant problem, these convolutions will become, you can Fourier transform and will become for you products. G retarded of omega equal to G naught retarded of omega plus G naught retarded sigma retarded G retarded. And now you see that you can solve for, it's an algebraic equation that you can solve for G retarded, and you will get G retarded equal to 1 over G naught retarded to the minus 1 minus sigma retarded. And this is what I wrote down before. Yes? No, no, there's no question. So 1 over omega minus epsilon naught plus I gamma minus sigma retarded. Now, a simplified version of what is sigma retarded. Sigma retarded is going to have a real and an imaginary part. The real part roughly is going to shift this energy level. Typically depends on frequency, but suppose that we can forget about the dependence on frequency. It shifts the energy level. The imaginary part, instead, is contributing to the width of the resonance, is giving what is known as an inelastic so I have a shift, and then I have an inelastic component of the width of the resonance, to the width of the resonance, because of the imaginary part of my self-energy. Whenever I have interaction, you should expect an extra broadening, due to the fact that you have interactions, right? So a particle that comes in does not necessarily come out at the same energy, because you can emit photons, emit something, leave behind particle excitations, and this broadens the resonance further. Well, if you have this guy here, this extra broadening, then these two expressions are not equal. In other words, if you have inelastic processes, then the T of omega that enters the formula for the conductivity is not equal to the absolute value squared of little t of omega. Why it is so? The reason is that this guy is actually only the elastic component of scattering. What this guy is telling you is what is the amplitude for a particle incoming at a certain energy, not to get out on the left, whatever, with whatever state, it doesn't really matter, but to get out exactly with the same energy. So it's the elastic component of scattering. And this one comprises both the elastic and inelastic channel. Okay? So it's quite natural that this is what should be sitting in the current and not the elastic one. And then you can ask me, okay, fine. So if I have an interacting system, will I ever be able to measure this in some experiment? So what should I do in order to measure the elastic component? Well, for example, one thing that I can do is do interference experiments. So one experiment that was done when I was young, it looks like a song, sounds like a song. When I was a student, was, so I'm drawing it roughly, so people were able to draw an interferometer in a two-dimensional electron gas. And this experiment was done by Moti Heiblum and others, and Amir Jacobi and others. And then they were shooting electrons, and electrons to go to the left could take two paths, one above and one below. And let's say that here I put a quantum dot. I put my resonant level. I put it here. Well, then, in this particular case, the term of the current that oscillates with the flux, that is the result of the interference between these two guys, turns out to be proportional to cosine of 2 pi phi over phi naught. Phi naught is the flux quantum, times the real part of T elastic of omega, which is the expression I wrote up there, times T star of the lower branch. So this is the transmission T lower, the transmission through the lower branch. So why do you have the elastic component here? Well, because in order to have interference, you don't want to leave anything behind, otherwise the path would be dephased. So that's why in order to, to catch proper interference between these two guys, you want to pick up only the elastic part of the scattering. So bottom line of all this physical discussion, if you have not, so you can describe transport as a scattering problem in a nanostructure. What matters for you is the transmission probability from the left to the right or from the right to the left. It doesn't really matter. If you have a non-interacting problem, you just compute it in the standard way. If you have an interacting problem, you have to worry about whether you're computing the total transmission probability or the elastic transmission probability. The first one is good for the current and for the conductance. The second one will enter any interference experiment that you will perform using any kind of interferometer you can think of. I mean, nowadays they do Mach-Zehnder interferometry and all sorts of fantastic things. And this was the simplest two-slit interferometer they used. Are there questions? Yes?
That high gamma that you defined when you are defining G0 and G0 retarded,
Yeah.
is that due to the interaction that
This one? No, this one is the usual gamma left plus gamma right. So it's the one due to the coupling to the leads, due to the tunneling. Okay. Yeah.
Does that enter into G0?
Yeah, it does. It does. It's actually G0 is, where is G0 here? So G0 retarded is 1 over omega minus epsilon naught plus I, gamma left plus gamma right. So it does, yeah. Okay, so now we are essentially ready to start. So all of this was physics. Now we start with Keldysh, which is physics, but a bit less physics. Right, so what we want to do now is to crank up our, artillery to figure out whether we can get that formula, the Meyer-Wingering formula up there. Okay? So that's the goal. And we're going to do it in general. So what I'm going to do is I'm going to deal with a problem in which I have a resonance. I have two leads with two different chemical potentials. And then I have some scattering region in the middle, and I compute I have some interaction in here. So my Hamiltonian in general is going to be made out of 4 terms. So one of them is H leads, which is the usual sum over K and I, epsilon K, C dagger, Ki, Cky. I apologize, here I'm using I instead of alpha for the left and right, but that's what I have in my notes. Then I have HD, which is equal to sum over M, epsilon M, D dagger M, dm. So in general, I have many levels in my guy, and then I have ht, which is equal to sum over k and I and m, v ki m of c dagger ki dm plus Hermitian conjugate. So these are the three terms, plus I have some interaction term. And the only rule of the interaction term is that I don't want it to involve operators in the leads, as I said many times already. So no operators in the leads. So now what I do with this? I have to compute the current. So as we had done last time, already 2 days ago, we can compute the current I as minus E n dot I, and then, well, this is equal to minus E over H bar, H commutator with Ni, and then, well, you do the commutator, you will get IE over H bar, sum over K and N, V K I N, C dagger K I N minus Hermitian, minus the complex conjugate. So you just have to do the commutators. It's not difficult. Right, so you see that in order to compute the current, what I really have to do is to compute this matrix element. I mean this average. And now I proceed in the usual way. I say, aha, this is the average I have to compute. And now let me connect it to a statistical Green function, right? So, and the way to proceed is to say, okay, this is equal to 2E over H bar times the real part of sum over K and N of V K I N G lesser N K I T T, where this Green function is Tt prime is equal to I C dagger Ki T prime dt. Okay?
What is that small a? CKI dagger?
Which one?
Yeah, that
This one?
No, the line before that. CK, the one within the box.
Ah, no, it's a D. It's a dn. Sorry. No, it's absolutely correct. It's a dn. All right, so you see that now I have to compute this Green function. So now I proceed in the usual way. So I say, I want to compute this. So let me introduce the corresponding contour-ordered Green function. Let me do the perturbation theory for that contour-ordered Green function. And then let me do the translation to get this. So this is the procedure. So first, I do the contour-ordered Green function. So I introduce C contour-ordered K N K I T T prime, which is equal to minus I T contour-ordered dn T C dagger K I T prime. This is my contour-ordered Green function. And now I look at this and I think about, let me imagine that I'm taking as H leads and plus H dot as my H naught. and ht plus h interaction as my perturbative terms in the Hamiltonian. And then I crank up the perturbative expansion. So what will I get in general? I will get that my full green function is equal to the bare green function. So this is the full green function. Oops, sorry, I have to write things more precisely because it's, where is it? So I'll have that this green function here is equal to, so the zeroth order term is going to be the green function n, then the tunneling vertex, and ki. See, because I have to enter as ki, then I have to destroy the ki and create an n. And here I will have the corresponding tunneling matrix element. So this is the simplest process you can have. Then, of course, you will have others that are similar, like this one. So the important thing is that ki is sitting here and n is sitting here. And what is sitting in the middle, I don't care. So I will have a lot of diagrams like this. But then I will have also diagrams in which I have the interaction. Okay, let me represent it as electron-electron interaction for simplicity. So interaction, what is important is that the interaction never involves electrons in the leads. Okay? So in practice, this means that, for example, this diagram will be there. This diagram will be there. Even this one might be there. But you will never get diagrams that have an interaction piece that involves this last green function here. You will never get it. And therefore, I can formally resum this series stating that this is equal to the full green function times this. Why? Because just by looking at these diagrams, I always notice that there is always this, appendix sitting here with ki at the end. And then all the rest, when it's summed, will give me the full green function of my, with indices n and m. Is it clear? It's just the structure of perturbation theory. Yes?
How do you understand these groups that you have drawn?
Oh, no, well, those I have to draw some interaction, right? So I told you, let me draw something that looks like an electron-electron interaction. So, but just for the sake of drawing something, I could draw an electron-phonon interaction if you want. I can do that. You want electron-phonon? So electron-phonon would be like this, and then like this, and then like that. It's the same, but whatever interaction you put there, the concept is that the interaction is never involving this line. And therefore, this line sticks out, and here is a full green function. And for me, what is important is to know that this is the structure of my perturbation theory. Okay? So is it clear to everybody? Right. So now, given the fact that this is the structure of my perturbation theory, now I do I take this and I say, aha, look at this. Very nice. This is equal to sum over m integral over the contour dt1 of g contour ordered. This is the full green function n and m t tau 1. N and m means I create a particle with index m and I destroy it as n. This is possible because I have many jumps to and from the leads, right? And then vkim star, and then gc ki tau 1 t prime. Okay? So this is the general structure of my perturbation theory. Now what I want to do next is I want the lesser. This is what I want. So I want to do I have to do the translation. So I have to take this, take the lesser component, which is the lesser component of this integral. But lo and behold, you see that this is just a convolution, so we can use the rules that I introduced yesterday to do the translation in 2 seconds. And therefore, what we get at the end is that g lesser of n ki t minus t prime is equal to sum over m integral dt1. This now is a real time. This becomes real time convolutions, v star kim. And then you have g lesser and m t minus t1, g advanced ki t1 t prime plus g retarded and m t1 g lesser ki t1 t prime. Yeah.
The interaction, the diagram from the interaction, there also the time integral is in the contour.
Sorry, can you repeat the question?
So when you usually add up these diagrams, you do it in the Fourier space, but here you're doing everything in the time.
Yeah, so here, when I write a C here, it means I'm integrating over the contour.
For the interaction diagram,
All on the contour, everybody on the contour, all of it. So this is all formally. You see, it's another way to explain this. The diagrams are like the instructions for Lego, right? So you watch the instructions. This tells you how to build your Lego, and now you have to take it to the real axis. But you know, that's how it works. It's very simple. You have your instructions, you write down the formulas, and then you translate it. Yes?
for clarification, why is the integral from tau 1?
What is?
Integral d tau 1.
Why here you have tau 1? Well, because you have this vertex here. So if you have a vertex, you know, imagine where it comes from. It comes from an S matrix that I expanded, and I took down, and I have an intermediate time because I take contractions, right? And then I have to sum over all the intermediate indices and intermediate times. So that's why. But this is a variable on the contour, okay? Okay. All right, so this is the final expression, and now we have to work with it.
And why does it become t minus t prime? Because
Well, again, I jumped forward again. But look, I'm interested in a stationary current, so it's time translational invariant. Yes? Are there divergences in diagrams? Sometimes, but not in this case. So when there are divergences, then you have to worry. And you have to worry also with Keldysh. Not saying you don't. But that is another subject. So if you want, the next time you invite me to here, and I'll give you a course on renormalization group. But today we stick to Keldysh. There might be divergences, okay? but not in this particular problem. All right, so what is the story now? Now the story is I have to introduce now this expression into my expression for the current that I don't know where it is, but you remember was the real part of this green function times some coefficients. So if you go through it, so let me see if I can get it. Oh no, it was not. I thought it was close in this direction. Okay, wait a second. We'll get there. Okay, that is the current, you see? So now I have to put the G lesser that I computed here, I have to put it there and take that sum. Okay? That's all I have to do. So if I do that, what I'm going to get is 2e over h bar times integral d omega over 2 pi times the real part of, I will have sum over k n and m of v k I m v star k I n. So this is n and this is m, and then I will have g retarded and m g lesser ki plus g lesser and m g advanced ki. Okay, so now I'm going to be as brutal as I can be. Okay, so I'm going to simplify a lot the calculation for the sake of making it understandable in simple terms. So the first thing I will do is I will, as I did yesterday, I will forget about the k-dependence of these tunneling matrix elements. You can put it back, it's not a big deal, but why do we have to complicate our lives for nothing, right? It's an effect, you can put it back. So if I do so, then you see that the summation over k goes straight to these green functions, because these are the only k-dependent terms in the expression. So let us do this summation. First of all, what is g lesser ki of omega? G lesser ki of omega, I already wrote it yesterday, but you can immediately write it just by using what I said is the fluctuation dissipation theorem. So it's a ki of omega, f of omega, fi of omega. And aki of omega for just a single level with no coupling to anything is just 2 pi I delta of omega minus epsilon k fi of omega. And therefore you see that if I compute sum over k g lesser, what I get is 2 pi I sum over k delta of omega minus epsilon k fi of omega. And this guy here is nothing but the density of states. Now, in principle, the density of states depends on the frequency, on omega. But let me assume that it's frequency independent, just for simplicity. In real life, it is frequency independent if the velocity of your particles is constant as a function of energy. So if you have a linear dispersion, well, which is the case close to the Fermi energy in one dimension, for example. So in that case, it works. Right, so this is going to be 2 pi I density of states f of omega I. Now, what about G advanced? G advanced is equal to 1 over omega minus epsilon k minus I 0 plus. 0 plus is the famous very tiny imaginary part that you put to regularize Berggruen functions. And now I get to compute the sum over k and I, sum over k, GA ki of omega. Now, well, what I do is I pass from the sum to the integral. So passing from the sum to the integral means I will have density of states integral d omega of 1 over omega minus epsilon k minus I0 plus. And then I use the Cauchy formula. I'm sure that you're all familiar with the Cauchy formula that is written usually in the form 1 over omega minus epsilon k minus I0 plus equal to principal part of 1 over omega minus epsilon k plus I pi delta of omega minus epsilon k. Right? Of course, it makes sense only under the sign of integral. Right? Now, the principal part integral, in principle, can be dangerous if you put here some bandwidth, right? And you're not exactly in the center of the band. So it will give you some shift, some real part. Again, let's take what people call the wideband limit, which means that you take these limits to infinity and you just forget about this real part. It's just a way to say, okay, look, I don't want to deal with this. So you say wideband limit is a short way of saying I don't want to deal with the real part. Okay? So I don't want to deal with the real part, and therefore this is I pi times the density of states.
So you're being prudent because you want to do something which is doable, and then
I want, look, all the, you know, it's like when you draw things, right? The first thing you do is a sketch, and then you paint the Mona Lisa. So here I'm doing the sketch of the Mona Lisa. And then you added the details of the eyes and everything else. But what I'm saying is that all these details are minor details. So you can add them. They will put some frequency dependencies here and there, complicate miserably your life. But at the end, the final result is going to be correct. So I'm just neglecting all the trivialities. All right, so now that we have done this, the final result for our current after we write down these two formulas is the following. The current is, wait a second, is EI over 2 pi. So here I already forgot h bar. I don't know where it is. Okay, h bar became equal to 1 in this formula. There should be an h bar somewhere. Well, somewhere there is an h bar. And then integral d omega, trace of gamma I, g lesser of omega, plus I have to explain this formula, fi of omega, g retarded of omega minus g advanced of omega. Right. So what is this expression? First of all of these guys are matrices. So when I write trace here, I mean trace in the matrix space in which the indices are n and m, the indices of the levels in my scattering region. Now, this gamma is the generalization of the gamma that I wrote yesterday. You see that there I have VIN, VIM times G and M, right? So the VIN, VIM, I can combine it to get the following expression. V star IM, and I call this gamma I and M. Okay? Now, these ones are the green functions GR or G lesser or G advanced and M, those matrices. This is the Fermi distribution, and you can easily prove that what I wrote there using this definition and these formulas here is identical to this. It's just simple algebra. Okay? Now we have this formula. This formula is for the current that is flowing out of the left lead. It's a bit upsetting, this formula, right? And there is something that is not good. This G lesser. Why it is upsetting? Because G lesser contains information about what is the occupation of levels in your resonant, in your scattering region. But why do you need that in order to compute the current? In principle, you can compute it just by looking at, what is the voltage bias. You don't need to know what is the occupation in here. Well, in general, you do. In general, you do. There are certain cases in which you can avoid dealing with this and therefore write a Landauer formula. So let me explain what are those cases. Imagine, so it is always true that the current that flows out of the left lead is equal to minus the current that flows out of the right lead. That's because I don't want to have charge accumulation within my scattering region. If I would have charge accumulation, then energy would slowly explode, so it doesn't make any sense. Now, if this is true, then it is also true that for each, you can choose x is a real parameter, such that I is equal, the current is equal to x times I left minus 1 minus x times I right. So you see, if you use this identity, you see that this is equal always. For each x is equal to the current, this weighted average. Okay? Now let me use this into using those expressions there for I left and I right. So what I get is that the current is equal to I times E divided by H bar times integral d omega. And then I'll have trace of x gamma left minus 1 minus x gamma right times G lesser plus x gamma left f left plus minus 1 minus x gamma right f right times G retarded minus G advanced. Okay, so now you see what is the trick. If, for example, imagine that I have just one level. So one level means that these are not matrices anymore. This is just a plain, real, complex number, right? If you have one level, there is only one n. So Gnm is G11, and there is only one green function and one gamma. So if there is only one green function and one gamma, then it's clear that I can choose x in such a way as to eliminate this term, right? And in particular, I will choose I will choose x to be equal to 1 over 1 plus gamma left over gamma right. And then, this term is gone. If that term is gone, then what I will be left behind, what is left behind is that the current is equal to E over H times integral d epsilon d omega f left minus f right. So this is what comes from this term times gamma left times gamma right divided by gamma left plus gamma right times A of omega. Which is the formula that I wrote down at the beginning. So you remember this is T of omega. Now, this is true if I just have one level. What about if I have more than one level? Well, you can still eliminate this term if it turns out that gamma left is equal to lambda gamma right. So if these two matrices are proportional, if the matrices of the couplings are proportional to each other, but have the same structure, then you can choose x to be 1 over 1 plus lambda, and then you can eliminate it and get the same result that I got here. The only thing that you will have to do is you will have to put a trace and interpret all of these as matrices. This is the only price that you have to pay. Right, so the bottom line is then, in almost all relevant situations, we can derive, using this Keldysh technique, a Landauer type formula for scattering that involves the total transmission probability, as I wrote it here. Now, this is not always true because there are certain situations in which the tunneling matrix elements, you have more than one level, and the tunneling matrix elements are combined in such a way that, well, I don't want to enter details, but because of interference effects, you have to know what is the occupation of your levels within the dot in order to compute the current. It's not charge accumulation, it's nothing special, it's just interference due to various channels that move inside the dot. Yes? Some question? No. But this is the end of the story, I think. So, yes? Here I'm taking a particular x, yes.
So if I choose another x, I will have a different formula.
Well, you will have a different expression, yeah, that is correct. But since at the end of the day, right?
Like it's a different current.
No, it's not a different current, because at the end of the day, if you choose a different x and you put it, so all of this story, if physics is physics and life and everything is correct, which I think it is, then you should get always the same current, right? Because I told you that I left is equal to minus I right, and therefore the current, which is I left or minus I right, is also equal to x I left minus 1 minus x I right.
The last line that you wrote, that I don't understand.
Which one?
That xil minus 1 minus xir.
You don't understand this, but this is simple, right? So this is equal to x times I left plus I right minus I right. But since I left is equal to minus I right, this is equal to 0. And this is equal to minus I right. So it's a tautology. I'm just writing a tautology. So provided, and this is something I didn't show. You have to trust me on this. Provided that this is true, and you have to, if you want, you can check it with the Keldysh formalism. But provided that this is true, then this linear combination will give you the same current for every x, every real x. And therefore, I can choose x arbitrarily, and I choose it, and this means that if I choose it in such a way to eliminate that term, I will get the current. So is it clear?
So you mean that there is some sort of relation between FL and FR, or maybe some integral?
No, it's actually the thing is, The whole thing is how you weight this term as compared to this term and this green function here. So eventually, I never did the calculation to, I'm not that, that precise, let's put it this way, to choose a different, what one could do in principle is put here a G lesser, do it for a non-interacting system. Put here your favorite G lesser, choose an arbitrary x, and see that the conspiration of these two terms gives you this one. And here I'm getting it with a trick. But the conspiration should always give you this one. So because here you're weighting stuff in a different way, you see, when you put a different x. It's not just gamma left minus gamma right. Is a different weighted average of these two guys. So it's a, yeah?
So, if you have a symmetry broken state in this way, where not just interacting on diagonal piece of the text function, is this generalized?
You mean a superconductor? Yeah, you can generalize it to superconductors. Yeah, I think you can do that. To be honest, I've never seen it done because typically for superconductors you study SNS junctions, not NSN junctions. But I think it can be done, and I think that at the end you will get something very similar to this. You just have to worry about the fact that, okay, let me go quickly through the calculation. Yeah, you will have to worry about the fact that when you do the decomposition that we have done at the beginning, you will have to deal with anomalous green functions there. So you will have an extra matrix structure which comes from anomalous green functions, CC, C dagger, sorry, DD, D dagger, D dagger. And then you will have, the, right, this is actually a good problem. You could put a Richardson model in between, right, and see what happens. I don't know. I mean, I don't know if people did it. It's actually an interesting problem.
Not relevant to anything because that's not, as you said.
Well, no, it's not true that it's relevant to anything. I mean, it is a very complicated way to study a transport through a superconducting grain, right? But it is relevant. I'm just saying I've never seen it done this way, because typically when people study transport through superconducting grains, they do it in a different way. They are not interested, but it's interesting. Okay, thanks for the question. So other questions?
For that particular x which makes it 0, so is there any physical meaning to it, or is it just mathematical?
No, I think it's, as I told your colleague, it's a mathematical trick. So there is no special meaning. You will get always this result irrespective to what is x. You will always get this result if you plug in here the G lesser and you combine these two terms. And since here, this is the lazy guy trick. So I wanted to get to the result as quickly as possible. So that's what I did. But this is the result.
This is a nice question, but why are you treating current and this gamma on the same
Current and gamma.
because you have I.
Oh, no, but that is clear because you see, the current up to the integration is gamma. So I is gamma I times G lesser. So the same combination that you get here will come out here because of this linear relation between the two, right? So that is quite obvious. Any other question? Yes?
The GR minus GA that you have, that's the rest is
GI minus?
GR minus GA.
Yes?
So why is the A like confused?
Oh, yeah, well, that's because it's the GA is the imaginary, is the complex conjugate of GR.
Why does it contain the information about the occupation of the dot?
Oh, yeah, well, it does. Right. So if you have an interacting problem, it does contain information about the occupation, right? So if you have a non-interacting problem, it doesn't. But if you have an interacting one, it does. You're absolutely right. So you cannot calculate it forgetting about the occupation. It will contain it, but it will contain it in a very, but it's there, right? It's there in a complicated way. It's sitting inside the self-energies. So the gamma inelastic will, of course, know what is the occupation. But you understand it here, everybody can understand this. If I have these two guys that have different chemical potentials, and my resonant level has a double-step distribution, right? It is clear that absorption and emission of phonons in this double-step distribution is going to be different than absorption and emission of phonons by just a single Fermi distribution. So life is going to be completely different, and everything is going to be sitting in that gamma inelastic, right? And by the way, this is actually so if any of you is super motivated, since some of you are super motivated, I'll leave you an exercise to do, which is the following. Imagine taking as H interaction d dagger d sum over q lambda q bq plus b dagger minus q. Okay, so electron phonon, well, kind of similar to electron phonon interaction. Now, when you have an interaction of this type, at the end of the day, all your calculations should be expressed in terms of the spectral function of your phonon bath, right? Which is defined as sum over q lambda q squared delta of omega minus epsilon q. So assume that you have equilibrium bosons from Bose-Einstein distribution, and this is the spectral function. Assume that the spectral function is ohmic. So it's theta of omega, absolute value of omega times some constant. So this is called ohmic dissipation. And now what you can do, essentially by computing the first corrections due to interaction to the green function of a single resonant level, which are just this diagram and nothing else, you can compute what is the current as a function, for example, of voltage, and show what are the corrections due to interaction, in particular the nonlinear IV characteristics. So write this as linear response plus nonlinear response plus etc., etc. And you will see that your interactions will enter here quite heavily, right? So yeah, so this is an interesting thing. Go to second order imperturbation theory in lambda, include this diagram in your calculation, and just do the calculation of the current. So the only tricky thing that you will have to do in this calculation is you will have always to think about reabsorbing all the interaction always in this form, right? So you will have to, to write everything in terms of this function here, because this is the only function that is characterizing, well, together with the distribution is the only function that is characterizing the distribution, okay? All right, so, okay, let's see where we are now. Okay, so let me now start with the setup of the next problem we will want to solve, and then we will solve it tomorrow. So the problem is, so up to now we have been dealing with time-independent problems, okay? And now what I would like to do is to show you how to use this mechanism to deal with time-dependent problems, with some kind of time-dependent problems. So in particular, one particular type of time-dependent problems that is perhaps interesting are the problems related to quantum pumping. Now, there are two types of quantum pumps. One type of quantum pump is the toweless pump. The toweless pump is based on the adiabatic theorem. So in order to describe it, just imagine that you take, for example, a charge density wave, and you plug some particles in the minimum of this charge density wave, and then you slide it very slowly through your system. Of course, you can create transport, but you have to go slow as compared to the gap, physical gap in your system, in such a way as to always stay in the ground state, right? So the toweless pump is based on the adiabatic theorem. What I would like to do now today is to describe pumps which are using as operating matter nanostructures of this type, right? So in which you have two leads, two metallic leads, and you put something in here and you do something. You vary your parameters, you do something else. Now, it is clear here, as I was mentioning to Shamik 2 lectures ago, that you cannot use the adiabatic theorem from the beginning, because your leads are two continua, right? So you are not in the condition to use the adiabatic theorem. Nevertheless, it turns out that you can describe pumping through these structures in a geometric fashion. And this was a major achievement quantum pumping. There was a major achievement of Pete Brouwer, who discovered a formula that we're going to derive using Keldysh, but he derived it in a different way, when he was just in his first year of postdoc. So now you know what to do, okay? In his first year of postdoc, he had this major discovery. It was really something very, very interesting. Now, now, the fact that you can pump a charge using these nanostructures is quite trivial, right? I can show you a cycle that does so. Imagine that I couple, first I have a resonant level that is sitting here. I initially couple it to the left, right? Then I disconnect it. I bring this guy up, so there is an electron here, and then I couple it to the right. Well, of course, this electron will go. So first came in, and then it goes out. And then I lower this level again, right? So this is similar to when you go with a bucket and you take water from the river. So it's a peristaltic pump, a trivial peristaltic pump. And it's pretty clear that you can pump charge using this trivial peristaltic pump. Now, what Pete Brouwer understood is that in general, for these systems, you can write in a limit that I will discuss in a second. You can write the pumped charge as, okay, this is not the original Brouwer formula, that is a bit more complicated, written in terms of S matrices and complicated stuff. I don't want to do it today. But he wrote it in this way. One way to write it is this way. So d theta of r dt 1 minus g of t. So what is this? I'm imagining that in order to do pumping, I'm taking two of the parameters of my system and I'm varying them along a certain cycle in parameter space. And then what Brouwer tells me is that, look, if you have a non-interacting system, the charge that you pump per cycle is E times the integral over the cycle of the derivative of the reflection phase. This is the phase of the reflection amplitude, times 1 minus the dimensionless conductance. So this is the conductance divided by 2 squared over h. So it's essentially the transmission probability. All right. So, well, first of all, this formula, perhaps you cannot see it, but it is geometric. It's fully geometric. It's independent on the parameterization of the path. The second nice thing of this formula is that it tells you is that if you are pumping along a cycle in which the dimensionless conductance is equal to 0 at all instants of time, then it is clear that this integral is of a full derivative. The reflection angle can wind up to multiples of 2 pi if you come back to the same state. And therefore, this charge is going to be quantized in units of the electric charge, right? And the quantization will depend on how many windings you have of your reflection phase. Right, so now what we are going to do now tomorrow, because it doesn't make sense to start today, is the following. I'm going to take the problem of transport through a generic nanostructure with time-dependent parameters and no bias between the leads. And then I'm going to compute what is the current that flows as a function of time and integrate it over a single cycle. And I'm going to show you, using Keldysh, that this current is given by a formula that is independent on the way you parameterize the cycle, or in other words, it's independent on the way you move along the cycle, but it's just dependent on what the cycle is. Now, this is true in what is known as the adiabatic limit. Now, adiabatic, not in the sense of quantum mechanics, because here the theorem is not valid, but adiabatic in the following sense, that I have two time scales here in this problem. One time scale is the time, so I can interpret gamma, the width of my resonances, as the average time, 1 over gamma, as the average time an electron is spending when jumping inside my scattering region is spending there, right? Because it goes there, stays there, 1 over gamma, and then goes out. So, and then I'm saying, well, if this time is much smaller than the typical time scale of variation of my parameters, which is the period of the pumping cycle, then this is it's a good adiabatic limit, as you will see in a second, in a certain sense, and then you can get the geometric formula. Okay? So this is the goal of next lecture. So do you have questions? Okay.